World War II raged across the globe, but behind the front lines, a secret race was underway, not for land, but for the power inside the atom. Scientists fleeing Europe warned the US that Nazi Germany might be building a bomb of unimaginable power. This fear sparked the Manhattan Project, a vast, secret network of factories and labs across America. The brightest minds, physicists, chemists, engineers, were united by a single goal: to turn atomic theory into a weapon before their enemies could. J. Robert Oppenheimer, a brilliant physicist, led this unprecedented effort. Under his direction, the project became a hub of frantic innovation, where new physics was invented on the fly. Every day brought new breakthroughs and the heavy weight of their mission. They weren't just building a bomb, they were rewriting the rules of science. The story of the nuclear bomb began with fear and scientific curiosity, not with an explosion. The Manhattan Project was a journey into the unknown, pushing human ingenuity to its limits. These scientists knew they were on the verge of changing the world forever. The question that haunted them: would this change be for better or worse? The universe had handed them the keys to immense power, and they were about to turn the key. The bomb's power came from two rare elements, uranium and plutonium. Forged in ancient supernovae, these elements are cosmic relics, stardust with explosive potential. The key isotope for bombs is uranium-235, a rare form found in only tiny amounts in natural uranium. Separating U-235 from the more common U-238 was one of the Manhattan Project's biggest challenges. Plutonium-239, on the other hand, doesn't exist in nature. It's made by bombarding uranium-238 with neutrons in a reactor. Both U-235 and Pu-239 are unstable. Just a nudge can split their nuclei, releasing immense energy. Their atomic hearts are packed with protons and neutrons, held together by powerful forces but ready to break apart. This instability is what makes them perfect for unleashing atomic energy. These elements are the keys to unlocking the energy Einstein's equation, E=mc2, promised was hidden in matter. With uranium and plutonium, the stage was set for the atomic age. The challenge was how to trigger their power. The secret to atomic energy is nuclear fission, splitting the nucleus of an atom. When a neutron strikes a uranium-235 nucleus, it splits, releasing energy and more neutrons. These new neutrons trigger more splits, creating a chain reaction that grows explosively fast. Billions of atoms split in a microsecond, unleashing a staggering burst of energy. This isn't a chemical reaction, it's a nuclear one, converting mass directly into energy. But to make it work, you need a critical mass enough fissile material packed together so the chain reaction sustains itself. Too little and the reaction fizzles enough, and you get a nuclear explosion. Controlling this balance is the heart of both reactors and bombs. The science was clear: fission could change the world. The next step was turning theory into a working device. The race was on to harness the chain reaction. With theory and materials in hand, scientists faced their biggest challenge: how to trigger a chain reaction on demand. The Manhattan Project developed two bomb designs. The uranium bomb, Little Boy, used the gun-type method, firing two subcritical pieces of uranium together to form a supercritical mass. The plutonium bomb, Fat Man, required a more complex implosion method. High explosives surrounded a plutonium core, compressing it instantly to supercritical density. This demanded precision engineering and perfect timing. The implosion design was tested at the Trinity site, creating the world's first nuclear explosion. These breakthroughs turned theory into reality and changed history forever. The atomic age had begun. The Manhattan Project was a massive secret industrial effort, employing over 130,000 people, most unaware of its true purpose. Entire cities like Oak Ridge and Los Alamos were built in secrecy, hidden from maps and the public. Producing fissile material was a monumental challenge, requiring new technologies to separate uranium-235 and breed plutonium. Enormous factories consumed vast resources, while nuclear reactors at Hanford produced plutonium under dangerous conditions. Secrecy was absolute, mail censored, travel restricted, and work compartmentalized. Scientists lived in isolation, racing against time and wrestling with the moral weight of their mission. Every breakthrough brought them closer to ending the war, and to unleashing a force they barely understood. The stakes had never been higher. The atomic bomb ended World War II, but it also unleashed a new era of fear and responsibility. The Cold War began, with nations racing to build ever more powerful nuclear arsenals. The science behind the bomb is a lesson in the double-edged nature of knowledge. Nuclear fission powers both weapons and reactors, offering both destruction and clean energy. The same science saves lives in medicine and threatens them in war. The Manhattan Project's legacy is a reminder. Knowledge is neutral, but its use defines us. Many scientists, haunted by their creation, became advocates for peace and nuclear control. Today, the world still faces the challenge of nuclear proliferation. Understanding this history helps us make wiser choices for the future. Knowledge is power, but only wisdom ensures our survival.